Moving on to the second lecture, okay, the last one on parallel circuit. How are current, potential difference, and the resistance related inside? Okay, so again, we go into the PHET. Right, this time round, I have a series circuit. This time round, I have a parallel circuit. So again, same thing, I have a cell, right, connected to the wires. Now in this case, right, one of this path, right, as imagine if you have the current flowing, okay, when I close it, right, you will notice how uh, the current, right, as it flows through this path is able to branch out into two separate paths. Now I'm not sure if you notice, but do you notice how fast the current is moving compared to the first video? Do you see that it actually moves faster? Now this actually tells us that the current here as compared to the previous component, right, it's actually much larger, okay, as evident from the speed. Okay, now because there are more than one path for the current to move now, we call this a parallel circuit. Okay, so these are the two resistors that are in parallel to one another. And afterwards, of course, this is a switch again. We can close it, okay, to take a look at how the current, or rather how the circuit looks like. So again, we're going to examine the current again. So if you notice, current now is much bigger. Now what does that tell you about the resistance? The effective resistance, okay, is actually higher, right? Sorry, the effective resistance must be lower for the current to be higher. Make sense, right? Lower resistance, more current can flow. So take note, if you look at now it's 1.8, right? What happens when I go to the first branch, right? It actually becomes 0.9 for the first branch. Okay, let me backtrack again. So imagine if I go to the second branch. Okay, because they have the same resistance for the resistors, the currents actually split themselves into half, right? Once they go through this connector. And then what happens is that the two currents, right, will meet again and they will combine back into the effective current. So what can you conclude from this? Right? What can you conclude about the current? Is that for parallel circuit, right? The current here and the current here, right? The current from the two branches will be the sum of the current, okay, in the total in sorry in from the total current from the part from the circuit will be equals to the sum of the branches. Okay, let's look at how the voltmeter, how the voltage will behave. So again, within the same wire, right, there won't be any potential difference because at these 2 points, they are at the same potential. So if I move down, you'll notice that it will still be the same. Right? What do you think is going to happen when I um, move the second point to somewhere here? What do you think will happen? Right? If I leave this one over here and then I move the black one to somewhere here, what do you think will happen? Will the voltage split as well? Okay, let's take a look. Right, you will notice that the potential difference actually is zero, which means that there's no difference in the potential. Okay, so in terms of potential, right, as long as there's no resistor in between, all each of the point will have the same resistance. So that tells us that there is no potential difference. Okay, until of course we pass through a resistor. And what do you notice? So if this is 9 volt, right, for this particular resistor, what will be the resistance, sorry, what will be the potential difference of the second one? Okay, now you will notice that actually they will give the same potential difference. And these two potential difference, right, compared to the EMF potential difference, right, they will be the same. So that's the unique point about a parallel circuit, whereby the potential difference at every point, sorry, not at every point, but across the component, right, the potential difference across component and the potential difference at the EMF is the same. Okay, what will this tell us about the resistance? Okay, let's look at it. Right, in terms of the summary, so the first one, right, now R1, the resistor, and the second resistor are in parallel circuit, okay, whereby the current is able to split path now. So that's why they are called parallel circuit. Okay, the current has more than one path to flow. And what's going to happen is that the current coming out from the cell, okay, the total current, will split at this connector. Okay, what this means is that the I total will be equals to I1 plus I2. Okay, so when it splits and then when it meets back at this connector, when it comes out, right, the total current will still be equals to the sum of these two separate branches. Alright, then afterwards, how would the potential difference be like? Okay, as evident from the video just now, the potential difference, so the potential difference for the first component, right, versus the second component, and then this is the potential difference of the EMF, right? That's why it's connected at these two particular points. So what this tells us is that VE will be equals to V1 plus V2. The potential difference, sorry, not V1 plus V2. V1 equals to V2. The potential difference is the same across the parallel branches. Okay, now to calculate the resistance. Alright, to calculate the resistance, so sorry for the break. Alright, to calculate resistance, now very simply put, if you are not interested in knowing how it's being derived, okay, very simple, it's just 1 over RE equals to 1 over R1 plus 1 over R2. So the reciprocal of the effective resistance is the sum of the reciprocal of each of the resistance. Okay, so I'm just gonna do a very quick derivation how I get this relationship. So I use uh, the result from the current, which is IT equals to I1 plus I2. So the current from the total the total current from the circuit, right, equals to, since V equals to IR, right, so I will just be equals to V total, or rather the EMF, divided by the effective resistance. So this is equals to VIR1 V2R2. Okay, now since the V EMF is equals to the V1 and V2, right, I can substitute inside. Okay, and since because these are all the same values, right, I can just divide VE on both sides of the equation. So when I divide, it just give me 1 over RE equals to 1 over R1 plus 1 over R2. VE divided by VE. Okay, remember this is one side of the equation, right? I can factorize the VE out. So when I factorize and divide by VE, the remaining result will just be this. So that's how I get the resistance, the relationship of the resistance. Okay, now for the summary, right? This shows us the advantages and disadvantages of arranging the electrical components in series or parallel circuit. So first of all, in series, the voltage across the bulb will become half, right? When it's connected to each of the component just now. So if let's say the two bulbs are having the same resistance. So for example, it looks something like this, right? So the potential difference across one of the bulb, right, will just be half. So because the potential difference is half, right, what this means is that the current and the current is the same at every bulb. If one of the bulb blows, the electrical path will not light up. Sorry. If the electrical path is open, then the other bulb will not light up. Okay, so if one blows, the other will not light up as well. As compared to a parallel circuit, right? As compared to a parallel circuit, if one bulb blows, right? If one bulb blows, it can still flow into the other path, completing the circuit. So the other bulb will still remain lit. Okay, and because the voltage across each of the bulb is the same, and the current will split across the component. So the bulb in the parallel arrangement will be brighter. Okay, why is it brighter? Again, it depends on the power, right? P equals to VI. So the V across the first component, in the parallel component, it's a bigger V compared to the series, and the current will also be bigger because if you take a look, the denominator here it's smaller compared to series. What this means is that, right, smaller denominator equals larger current value. Okay, that's why the bulbs in parallel will be much brighter. Okay, now what happens if let's say I add in more parallel branches? So I continue to add in more branches below, right? This could result in the overdrawing of current from the power. So the power source, okay, depletes more quickly. So the battery will run out faster, right? And if the circuit requires constant current, parallel connection should be avoided. Okay, next one, right? Now, the parallel circuit ensures that if one bulb blows, the rest of the bulbs are not affected. So that's the key advantage of parallel, but the power source will be depleted more quickly. So do you think your electrical components in your house, are they connected in parallel or series? Right? Think about that. So let's look at work example 2. Let's calculate what is the effective resistance of the following parallel circuits. Now, so if you look at this is a component of, there are three components, two of which connected in parallel, and then they are both connected in series with the 4 ohms. Right? So what this means is that it will be the same as if I connect to one uh, resistor that has the effective resistance of these two in parallel, right, with the other 4 ohm resistor. So what would be this effective resistance? What would be the effective resistance of this resistor? Right, it will be, so let's say if I call this R1, right? So R1 would just be 1 over 3 plus 1 over 6. Remember, the effective resistance of parallel is calculated in the reciprocal. So let me type in my calculator. One third plus 1 divided by 6. Okay, 0.5, right? But that is 1 over R1. So what will be R1? R1 will be 2 ohms, right? So this will be 2 ohms. So since there are two of which in a series arrangement now, this is the same as if I sum up the resistance together. Okay, so the effective resistance here will be 6 ohm. Okay, next one, again, if you look at these two resistor, 3 ohm and 4 ohm, they are both in series to one another, right? But both of which are parallel to the 6 ohm. So we can simplify this circuit diagram again into the effective resistance of two components like this, right? One is the 6 ohm. So what will be the effective resistance from these two resistor? Right, 4 plus 3, that will be 7 ohm. Then since this 7 ohm is in parallel to 6 ohm, right, in terms of the effective resistance, so RT, 1 over RT equals to 1 over 7 plus 1 over 6. Here's my calculator. Right, this will give me 13 out of 42. So RT will just be flipping it again, 42 out of 13. Okay, 42 out of 13 in terms of the 3SF, 3.23 ohm. Okay, Sorry, I should move it up. Okay, if you've written it down inside, it's fine as well. So RT equals to 3.23 ohm. Okay, last example. Let's practice 14.2. Look at the first one. Figure 14.19 shows two resistors connected in parallel. Calculate the current flowing through and the potential difference across each resistor. So if it's parallel to 1.5 volt, what would you think is the potential difference for each of the cell? For each of the resistor. Okay, since it's in parallel, so potential difference across the difference across 3 ohm, right? Or you can just put a V subscript 3 ohm. That means the same thing. Plus 1.5 V of 1 ohm equals to 1.5 volt as well. Right? What do you think will be the current flowing through? First of all, I have the since I have the potential difference, I have the resistance of each of the component. I can find the individual current. So the current flowing through the first one, for example, first component, V equals to V1 over R1. So V1, which is the 1 ohm, is 1.5 divided by R1. So this gives me 1.5 ampere. I2, V2 over R2. So this is equals to 1.5 volt divided by 3 ohm. So this gives me half ampere, which is 0.5. Okay, so if there's an extension question where they ask what will be the total current flowing through the circuit, right? It will be the sum of these two. Okay, next one, determine the EMF of the cell in 14.2. So over here, because there is a 12 volt over here, sorry, what is this now? Oh, they are measuring this is really the potential difference across uh, these 2 points, right? The potential difference across the parallel branches. So I know this is 12 volt, right? Potential difference of this and this is 12 volt. Okay, so does this mean that the potential difference across this component also is 12 volt? May not be, because again, this is these two components are parallel to one another, but these two together is series with this component. Okay, so it may not be 12 volt. So part 2, okay, I can find what is the current first running through. I should find what is the I1 and I2 first, so that I can find what is the current that's running through this particular component. So I1 equals to V over R. So V1 is 12 volt divided by R1, 12 ohm. Okay, this gives me 1 ampere. Then I2 will be equals to V2 over R2. So V2 is 12 volt divided by R2, which is 6 ohm. Okay, should I write this? Should I write this? So this gives me 2 ampere, right? So from these two branches of current, I can find what is the total current coming out from the main circuit, the main branch. So I equals to I1 plus I2, 1 plus 2, 3 ampere. So since I know what is the uh, current from the main branch already, I can find what is the EMF from the cell. So the EMF from the cell will just be the current from the main branch times the effective resistance. Right? I can find what is the effective resistance. Okay, there's another way that you could done it also. If you don't choose it to do this way, we could also find what is the potential difference of this 1 ohm. So the potential difference of this 1 ohm will just be equals to I times R. Okay, I which we already found 3 ampere, 3 times 1, 3 volt. Okay, so again, because this is this component and this component, they are series to one another. What this means is that the potential difference will just be the sum of these two components. So VE equals to V of the 1 ohm plus the V of the two components in parallel. Okay, so this will be 3 plus 12, 15 volt. So that's the EMF, right? So you may pause at any point in the video to take a look. Okay, so this is what we have covered in the DC circuit. So DC circuit, DC, it just means direct current. So another uh, part of it, right, is actually something called alternating current or alternate current, AC current. So I'm not sure if you've heard of it, AC. Okay, it's another branch of physics. Okay, so DC talks about series parallel, how would the EMF, how would the potential difference, how would the current, and how would the resistor, effective resistance behave. Okay, series and parallel. Okay, this is a key summary. So for series, current at every point is the same. Potential difference is the sum. Effective resistance is also the sum. For parallel, current is the sum. Potential difference is the same. The effective resistance is the reciprocal, sum of the reciprocal. Okay, knowing the advantages and the disadvantages. Right, that's all.